floor is yours.
Good evening, everyone. I'm Moussa Kafal. I'm a research engineer at the French Alternative Energies and Atomic Energy Commission in France. On behalf of Josie, my colleague, and I am going to be presenting today our presentation, which is going to be entitled as TDR FDR technique for the evaluation of aging of MPP cables. Okay, first of all, I'm gonna just start with a brief introduction. Okay, presenting the institute or the research institute that we are working for. As I already said, we are working at the CEA, which is the acronym of the French Alternative Energies and Atomic Energy Commission in France. It is the most innovative public research organization in Europe, according to Reuters scientific evaluation. It has been scored as the second best global innovative institution in the world, and it is a key player in research, development, and innovation in four main research and industrial areas. The first is defense and security, where CA is responsible for developing concepts for the army, in addition to technical security and support for the authorities. We are also integrated and interested in developing low carbon energies, whether nuclear energy or renewable energies. These include wind turbines, solar panels, and hydrogen based technologies. We also do work in the division of fundamental research in the physical and life sciences areas, notably in biology, genomics, astrophysics, theoretical physics, and modeling of corresponding systems. And last but not least, which is one of the recent research divisions established at the level of the CEA, which is the technological research for the industry, which is responsible for the valorization and the transfer of knowledge, skills, and technologies to the industry. In other words, this department or this division that we work for, which is the technological research division, is responsible for filling the gap between the theoretical research developed at the level of universities and theoretical laboratories and the industry, which are more interested in practical implementation of such ideas. At the level of TA, we are around 15,000, or let's say more or less 16,000 employees, okay, with permanent contracts, an annual budget of around $6 billion, and we were capable of patenting around 762 patents in the year of 2018. CA have succeeded in spinning off around or more than 141 startups in different areas and domains. Okay, we have more than 51 research units and more than 600 industrial partners across France, Europe, and the world. CA has more than 500 PhD and postdoc research assistants. We had around 424 European projects in the year of 2018, with more than 4,000 publications, okay, in terms of conferences and journal papers in the year of 2018. CA maintains several campuses in France. Okay, the biggest is in the Parisian region in Saclay. Okay, and the second one is in Grenoble. Other parts of France have smaller sites of the CA. So, CA main missions, as we already said, is scientific excellence. Okay, in fundamental research, defense and national security, energy independence, and industrial competitiveness. Okay, with three main laboratories. Okay, the first is the micro nanotechnologies laboratories. The second is the new energy technologies, and the third is the smart digital system. Okay, our mission is to create and transfer innovation to the industry with while looking for long-term partnerships, results oriented to address the partner issues, and project oriented, reactive, and flexible. The main two laboratories which handle technological research are the LIST and the LETI division, which work on the design, architecture, and embedded software. They have more than 300 multidisciplinary researchers with the industry, with good research and industrial background. 50 patents, around 50 patents per year, and more than 100 scientific papers published per year. Um, as I have already said, we are working on diverse research topics, okay, in technology and in the industry, okay, starting from the summation fusion, which is a low power real time sensor fusion processing system for LiDAR data of autonomous car applications, retina smart imager, which is an electronic retina, which enables smart, independent, and local image processing, pressure measurement ribbons, which are ribbons produced at the level of the CEA, which are high density 16-bit pressure measurement ribbons with 10-bit thermal compensation for airflow characterization, low noise imager, safety, and many core technologies, in addition to the thematic or the working domain, which is the work that Josie, I, and our colleagues work on, which is the cable diagnosis. Okay, this cable diagnosis is one of two thematics worked at the level of the laboratory of reliability and integrated sensors, which is the lab that we are working at. It develops technologies, okay, for detecting and locating faults, okay, within reduced footprint, power consumption, and cost. Okay, the laboratory, okay, have three, let's say, main working fields: radiation of hardened electronic system design, analog digital electronic systems and processing for state-of-the-art sensor integration, health monitoring of complex transmission line networks, which is the interesting working domain that we are going to be presenting today. We are 16 permanent research and development engineers, 2 part-time research and development assistants, and 3 PhD students. So, going into or going deeper, okay, in the cable diagnosis, you can well see that it is a major challenge in many applications. Okay, throughout the past few decades, okay, cumulated lengths of cables have increased in different applications. Okay, where modern cars contain something like 4 kilometers of cables, okay, for data transmission and for energy transmission, 400 kilometers in civil planes, and this could reach to more than 50,000 kilometers in the power grid of a country as France. Okay, these cumulated lengths of cables are gonna encounter, okay, one day or another problems, okay, related to diverse, okay, internal or external conditions. Okay, this is gonna lead to the appearance of something referred to as faults. Okay, faults are usually categorized into two main families. We have the main family of hard faults, okay, which is characterized by either having an open or a short circuit, and any other alteration that can affect a cable is known as a soft fault. These include insulation damage, cracks, and freeze. Unfortunately, soft faults, okay, are gonna deteriorate with time, okay, leading finally, okay, or eventually to hard faults. These are gonna lead to, let's say, negative consequences, whether at the human level, okay, leading to casualties as in aircraft crashes, in fires, and to economical losses, whether in property damage, scheduled delivery delay, or mission aborting. Okay, so as I already said, a soft fault is gonna deteriorate with time, leading to a hard fault. Okay, in the figure or the set of figures on the top of the slide, you can see that a slight insulation damage has deteriorated with time, okay, to not only affect the insulation of the cable but also reach to the internal contact of this cable. A lot of techniques have been innovated throughout the last decades in order to diagnose and try to detect and locate different kinds of faults within transmission lines and cables. Okay, these include the prognostic fault detection, okay, which have visual inspection, okay, radiographic inspection, low frequency and DC methods, capacitive methods, in addition to medium and high frequency methods. A lot of these methods have shown to be time consuming, highly expensive, and inefficient in most of the cases. Okay, so there was a real need for novel technologies which are dedicated to accurately locate faults in cables. Reflectometry based techniques have been in the center stage of research and industrial applications in this domain and have shown effective results in terms of precisely and accurately detecting and locating faults in different configurations of transmission lines, whether in communication networks or in power networks. So what is reflectometry? Reflectometry is a technique, okay, which is adopted from the concept of radar. Okay, I guess most of you are well familiar with a radar where a signal, okay, is emitted in free space, okay, and once this signal encounters a target, okay, it's going to be reflected back to the radar, okay, or reflected back throughout the medium, okay. The analysis of this reflected signal is going to give us an idea, first of all, about the location of the target, okay, where the distance to the target can be easily computed as the round trip delay, okay, divided by 2, okay, multiplied by the velocity of propagation of the electromagnetic signal that has been emitted, okay. So the most general approach to evaluating the time domain response of any electromagnetic system is to solve Maxwell's equation in the time domain. Okay, so in order to transmit a reflectometry signal, two conductors are usually needed. Okay, so the transmission line theory provides an analytical description of the propagation of electromagnetic waves along the lines. Okay, so the solution of these Maxwell's equation are usually done with telegraphs equations. Okay, these are gonna enable computing the propagation constant of a line and its corresponding characteristic impedance. This is a simple architecture showing the system, okay, which is capable of applying reflectometry, okay, to a wiring network. Okay, first of all, we have an arbitrary waveform generator, which is gonna be used in order to inject a predefined signal into the network to be tested. Okay, this signal could have different forms, okay, depending on the network to be tested and its circumstances. Okay, that is its frequency and its level. Okay, so if you wanna test a short, okay, length network, okay, we would be applying testing signals having very high frequencies. Why? Because we need to have a good resolution. Okay, otherwise, if we want to test long distance networks, okay, we're gonna have to decrease this testing frequency in order to mitigate, okay, the effects of attenuation, which increase as a result of increasing frequency. So a TDR signal or testing signal is sent to the network. This signal is going to propagate along the network and it's going to be reflected, okay, at extremities, junctions, okay, extremities, junctions, and discontinuities or defects. Okay, the analysis of this reflected signal is going to be plotted in the form of something referred to as a reflectogram. Okay, so the reflectogram usually plots the TDR response or the reflected signal which has occurred as a result of a testing signal injected at one of the extremities of the network. Okay, so the reflectogram on the right, okay, shows different, okay, responses due to different impedances. Okay, normally for an open circuit, okay, a positive peak is obtained. Okay, so for a hard fault, which is an open circuit, a +1 should be obtained. Okay, for the worst case of a short circuit, a -1 is going to be obtained, and then between these two values, okay, the intensity of the fault is going to determine the magnitude or the intensity of the peak. Okay, so the smaller the intensity of the fault, the lower the peak. Okay, several TDR or several reflectometry variants have been developed, okay, depending on the domain of analysis. We have the time domain reflectometry, which eventually shows that the reflected signal is analyzed in the time domain. We have the frequency domain reflectometry, where the reflected and the tested signals are analyzed in the frequency domain. And we have finally a new variant of the reflectometry techniques, which is the joint time frequency domain reflectometry, which uses both the time domain and the frequency domain analysis. Reflectometry has successfully enabled fault localization. However, it is um, affected by several challenges, starting from the electromagnetic environment being environmentally sensitive, that is the presence of noise, perturbations, etc. in the measurement environment, okay, the signal to noise ratio, and a trade-off of the accuracy to range. As we already stated, in order to be capable of having a good resolution, the frequency of the testing signal or the bandwidth should be increased, okay? But increasing the bandwidth or the frequency of the testing signal is going to be accompanied by increasing the attenuation and the dispersion along the cable, okay? So a trade-off should be done between the resolution and the range of the tested network, okay? In the timeline, okay, reflectometry first appeared in the 1971, okay, where stepped light pulses were injected. The figure on the right, or the photo on the right, shows one of the preliminary devices that have been used in order to apply reflectometry. Okay, it was developed by Tektronix company, and it used a 200 millivolt pulse, which with a rise time of 25 picoseconds. Okay, when I was talking about the resolution, okay, and the range, okay, I guess it is important to just show their relations, okay, where the time or the rise time, okay, shows that the higher the frequency, the better the resolution. The testing range is given by 1 over the delta f. Delta f is the frequency step multiplied by the velocity of propagation, and the TDR accuracy is thus affected by the reference impedance, the baseline correction, cable losses, and the noise. Okay, with time, several variants have been developed. Okay, in 2005, the SPET spectrum time domain reflectometry has been developed. Okay, it uses sign modulated PN codes. Okay, it has a high immunity against noise, suited for live wire testing. Okay, for those who do not know what is live wire testing is testing a network while it is in its live operation. Okay, so if we assume that we are testing, for example, a power network, this means that the power network is not shut down. Okay, it's in normal operation, and we're going to apply some kind of testing signal which do not have interference with the already present signals on the line. Okay, in 2009, MCTDR, which is the multi-carrier time domain reflectometry, has been developed. Okay, it uses weighted sums of sinusoids. Okay, it has good interference cancellation, good spectrum control, and good for online diagnosis. Okay, in 2013, a variant of the MCTDR has been also developed, which is based on OFDM-based signals. It has shown to be efficient in online diagnosis, good against interference, has a good bandwidth efficiency, and allowed complete spectrum control. Okay, the most important point is that it has also allowed sensor communication. What is sensor communication? Sensor communication is accomplished in the case when you have ramified networks. That is, networks which are composed of several branches, okay, and several extremities. In this case, applying the standard reflectometry is going to be confronted by multiple reflections, and thus we could have ambiguity on localization. In this case, OMTDR allowed installing several reflectometry devices at different extremities within this network, and a communication protocol has been defined in order to communicate data between these sensors to enable precise and accurate localization of faults. Okay, in 2016, chaotic time domain reflectometry has been developed. This technique showed high performance in very noisy environment. It was also good and compatible for testing live networks. There was no need for spectrum control. It has been shown to be inexpensive and suitable for testing intermittent faults. Intermittent faults are some kind of hard faults that appear and disappear in very short time durations. Okay. Our lab, okay, has successfully been capable of designing the last three reflectometry techniques, okay, the MCTDR, the OMTDR, and CCTDR, and we have recently developed a technique referred to as the binary time domain reflectometry, which is still in the progress of developing and testing. Okay, um, it should be noted that the MCTDR technology, which has been patented at that time, is now part of a startup company which has spinned off from the laboratory. Okay, so time domain reflectometry had been effective in several applications. Okay, it has been applied for detection of hard faults, open and short circuits. Okay, it has enabled cable characterization, that is extracting RLCG parameters of these cables. Okay, it has also enabled the soft fault detection. Okay, it also enabled distributed diagnosis, that is applying several reflectometer devices at different extremities of the network in order to increase the accuracy of detection. Okay, it also have been applied with success for the detection and location of intermittent faults, that is faults that appear and disappear in fractions of milliseconds. It has been recently applied for temperature sensing. Okay, and temperature sensing, we are recently working on a project where some kind of sensitive cables, okay, which are designed, okay, that are capable or that do change their impedance, okay, as a function of the temperature. Okay, so in our case, TDR is applied in order to determine the increase in the temperature in some portions of these cables. Okay, we're going to be showing these application afterwards in the presentation, and it has also been applied with success for aging detection, that is detecting the useful lifetime of a cable. Okay, in our laboratory, okay, we have applied also the reflectometry, okay, using several analogies, okay, using the VNA or the vector network analyzer, which is a device based on the frequency domain reflectometry technology. It sends okay, set of sinusoids, okay, and it is capable of having wide bandwidths, thus enabling high resolution um, detection. Okay, um, in this slide, okay, or in the coming slides, I'm gonna be briefly explaining the technologies of the time domain reflectometry that we have been working on. I'm gonna start with the multi-carrier time domain reflectometry. As I already said, it uses some of sine curves, okay, as shown in this figure. Okay, and these kinds of signals are usually injected, okay, in the network to be tested. This probe signal spectrum is controllable, okay, by canceling the desired carried signal as shown in this figure. So this technology or the MCTDR has enabled spectrum control, that is testing the network, okay, in bands where the network is not operating. Okay, it has shown electromagnetic compatibility. It has shown to be a low. It has shown to be less sensitive to noise. Okay, and I guess it's now in the TRL 4 range, okay, of testing. Okay, the OMTDR, as I said, it's the orthogonal multi-tone time domain reflectometry. Okay, it has been inspired by the OFDM communication protocols. Okay, the injected signal is composed of a selection of sine frequency subcarriers, and the data can be encoded using subcarriers, okay, PSK, phase shift keying modulation. Okay, it has proven key benefits versus standard TDR in terms of allowing communication capabilities between sensors. This enables the analysis of faults from several injection points, as I already said. For example, in this network, as you can see, this is a kind of a ramified network, okay, where you have several junctions and several branches, okay. In this case, okay, just as to show a short example or a brief example about the ambiguity, in case we are using a single reflectometry device, okay, the presence of a fault at this location or at this location at the same distance, okay, will not enable the reflectometry testing device of knowing at which branch the fault is located, okay. The sensor or the reflectometry device is capable of referring the distance from the testing port, but it's not going to be capable of inferring the branch at which the fault is located. So in this case, okay, there is a necessity of using multiple reflectometric devices, okay. OMTDR has enabled a good communication between sensors so that one sensor is going to be a master sensor and is going to communicate data and result with slaves or other reflectometry devices present at other extremities of the network, so that to give an accurate localization of the fault in terms of distance and precise location, okay. It also allowed frequency bandwidth control since it's based on the OFDM principle. This means that subcarriers could be implemented at multiple frequencies on guard bands where the system or the original system is not operating. As we have already said, our laboratory was capable also of applying different reflectometry variants for soft fault detection, as you can see on these two figures. Okay, we have applied OMTDR and the MCTDR for chafing faults. Okay, as you can see, they are not that major faults. The reflectograms show different signatures, okay, of the faults. Okay, and at different levels of the fault. Okay, we have applied some kind of post-processing approach in order to amplify the signature of the fault. Okay, because normally for these kinds of faults in long cables, the signal is the one shown in purple. Okay, so we applied some kind of amplification algorithms, and we, as you can see, the signature of the soft fault has been vastly amplified and it is much more visible. Okay. We have also developed at the level of the laboratory Hydra. It's an adaptive RTL platform for reflectometry. Okay, it has been generic. Okay, where the library of the RTL IP is used for data generation, acquisition, and processing. Okay, generic parameters at synthesis and online adaptation, specific adapters to comply with external components, and specific state machine for a default detection decision. Okay, the targets were the FPGA and the ASIC controllers, okay, and it has interfaces with the different electronic components. It had a good performance on a 50 megahertz FPGA. It was capable of detecting intermittent faults with appearance periods of less than 10 microseconds, and it has produced a fault location accuracy in the range of 6.5 centimeters. Okay. We have also developed the faster, okay, which is a method based on time reversal. Okay, it's a variant of it's an acoustic radar method or post-processing approach. This method or the time reversal has been, let's say, merged with reflectometry in order to be applied with or for the detection of faults in power networks. In the case of power networks, it's important to show that in high voltage and medium voltage transmission lines, faults are usually active. In other words, the fault itself is emitting a signal. Okay, so in the case of faster, what we did is that we were only listening at the level of the network. Okay, we didn't inject any signal. Um, uh, we were putting or installing some kind of couplers, which are either inductive or capacitive couplers, and we were recording the signals generated by the faults. These signals have been then post-processed using the faster algorithm, which is the algorithm based on time reversal, and we were capable of detecting faults with a location error of less than 3%. Okay. Um, we have also, let's say, adapted, okay, reflectometry with
Sorry, Musa, just to tell you that you have 10 minutes left.
okay. Okay, that's fine. Okay, we have also merged reflectometry with IoT applications. Okay, in other words, we have applied intelligent sensors which are capable of using, for example, a communication network of transmitting data recorded at the level of the network to some kind of database where these data are then processed, okay, with certain post-processing approaches, and some kind of signals are to be transmitted to maintenance operators in order to be capable of knowing the location of a fault in any of the tested networks. We have also applied reflectometry to the topology reconstruction. That is, briefly, okay, for a network. Okay, this is a just a scheme. Okay, for a network which is embedded in a black box where we know nothing about its connections. We developed a reflectometry-based algorithm with optimization algorithms, which was capable of extracting different parameters of the network, notably its topology, its branch lengths, and the impedances connected at its extremities. Okay. Reflectometry was also applied in a contactless configuration, okay, where the injected signal was injected in a contactless manner to the cable to be tested, and effective results have been obtained. We also applied 3D modeling of cables and applied that with reflectometry techniques, and that was also a success. This is one of the boards that we have developed at this at the level of the lab. This board is the board which is capable of applying OMTDR techniques in order to detect faults in communication networks. As I already said, reflectometry has been used in order to extract the parameters of a network to be tested, and this technology has been known as the R2 RLCG technology. It was capable of extracting different features of the network to be tested, and it has allowed aging monitoring. Okay, Josie, if you want, you could take the floor in order to continue this part, or Josie.
Okay, okay, Musa,
Yeah.
I let you continue. Okay, okay, let's continue.
Okay.
Continue you, Oku. Okay,
Yeah, yeah, it's okay.
you prefer. Okay,
Yeah, yeah, so it's
as
up
you
to
want.
you. Yeah, okay.
Okay.
So as I already said, we were capable of monitoring the aging of cables, and that was accomplished by the extraction of the RLCG parameters from frequency analysis. Okay, so how was this done? Okay, first of all, a TDR or an FDR measurement of the cable from one extremity has been done. We applied a model fitting algorithm. Okay, where this model fitting algorithm was capable of estimating the L and CG parameters of the cable, and a qualification against reference reflectogram data was applied. Okay, so as you can see, okay, this enabled, okay, determining the aging effect, okay, with respect to a reference model of the cable. Okay, so in this case, we have applied the RLCG extraction algorithm, okay, against a cable, okay, after applying some kind of aging techniques to it, okay, and as you can see, the GLC parameters, okay, of the aged cable have shown the aging effect. Okay, this has been translated in terms of attenuation, in terms of a difference in the wave velocity, and in terms of a change in the characteristic impedance. Okay. Okay, so this and then the R2 ZC profile algorithm has been developed. Okay, this was done in order to extract the characteristic impedance profile of the cable. It follows the totally the same analogy as that of the R2 RLCG. Okay, where a model fitting algorithm is applied. Okay, in order to quantify, okay, the ZC profile, okay, we have computed sort of an error, okay, which is given by this equation, okay. It determines or it computes the ZC profile, okay, result from the aging cable, and that from the estimated one from the algorithm. And as you can see, we have applied this algorithm with simulation, with laboratory tests, and with real cables. Okay, in this case, we have applied the algorithm at a frequency of 200 megahertz. Okay, and as you can see, we were capable of extracting. Okay, this is a theoretical profile. Okay, and in the red, it's the profile obtained with the method. Okay, we were capable of retrieving the characteristic impedance profile with an error of less than 5%. We applied the same algorithm with a much higher frequency. Okay, as I already stated, that higher frequencies enable higher resolution. Okay, this is translated in terms of the reflectogram. Okay, as you can see, this reflectogram is computed at 200 megahertz, and this reflectogram is computed at 8 gigahertz. Okay, it can be seen that a much better resolution is obtained, and this is also translated in terms of the ZC profile, where an error of less than 1.5% have been obtained. Okay. I guess these are somehow the same results, but with applying sort of connectors to the networks. In this case, for example, okay, at a relatively low frequency of testing of 200 megahertz, we were capable of extracting the ZC profile with a precision of less than 0.35%, which is indeed a good, let's say, a very good result at such low frequency. Okay, whenever I say low frequency, this is translated in terms of reflectometry, because normally reflectometry is a high frequency technique that is usually operated on bandwidths in the range of gigahertz. Okay. We also applied the technique, okay, on a cable with an aging in its middle. Okay, and we have also been capable of retrieving the ZC profile, okay, of the theoretical one or of the reference cable, and that of the one with the aging. As you can see, we have obtained a slight difference with an error of less than 3.1%. Okay, and with the method, we retrieved a 3 centimeter local aging, okay, at the simulator, as you can see in the figure. The same approach was also applied at higher frequencies, and the same accuracy was obtained. This means that this shows that the algorithm has presented good performance at low and at high frequencies in terms of retrieving the ZC profile of the cable and localizing the aging region within the cable. We applied the algorithm on laboratory cables, okay, of different types. As you can see in this scheme, okay, we have used two different types of cables having two different characteristic impedance, 50 ohm and 75 ohms of different lengths, okay. And we applied the reflectometry technique first at a 1 gigahertz bandwidth of test, okay. And as you can see, we have obtained a relatively very low error, which is around 5.1%, which is an average, which was the maximum error obtained. And as you can see in the table, okay, these were the theoretical ones and the retrieved values obtained. Okay, we also applied the algorithm on project cables, which are severely aged in an oven by UAVs, okay, where a 150 degrees Celsius temperature was applied for 3 weeks, okay, in order to apply an accelerated aging on these cables, okay. This was the network of the cable tested, okay, and as you can see, the method or the TD or the R2 ZC profile algorithm has been capable of precisely determining the regions where the cable have been aged. The same result was also applied on different kinds of cables in order to monitor, okay, different the effect of the algorithm and the performance on it using different kinds of cables. And as you can see, and we have tested this network, and also good results have been obtained. Okay, this, for example, this reflectogram shows the case where no aging is obtained. In this one, partial aging, and in this one, we can show that full aging has been applied. In this case, the FDR and TDR measurements on long cable samples aged in the Panosa facility in the Czech Republic. Okay, these are real cables which have been aged inside a facility against radiation and different temperatures. Okay, we have applied the testing approach, okay, where we have used a VNA for the sake of measuring the TDR and the FDR responses of these cables, as you can see in the figure. And these are the configurations of the two network that have been tested, and different portions that have been applied with the temperature increase and that of the irradiation. And applying the as you can see, applying the algorithm have shown that good performance have been obtained in terms of determining the aging parts of the cables. We have realized that we obtain a more aging effect when the temperature and radiation increase. Okay, so these figures show the results obtained, okay, with the aging impact. As you can see, we have obtained a decrease, okay, in the peak of the response when the dose rate, okay, or the temperature increases above 86 degrees Celsius, which is evident. Okay, the same has been shown, okay, in the second figure at different periods of the aging. As you can see, okay, this were the times when the aging have been applied. In this case, with these are the results also obtained for a black pearl outside the thermo, okay, where we can also see a decrease when the dose rate increases at a fixed temperature of 46 degrees Celsius. And as you can see here, this is the aging effect, okay, leading to echoes, okay, and in the form of a soft hold. This plots the FDR response, okay, in order to monitor, okay, the aging effect. As you can see, instead of obtaining a flat line, we have obtained different levels, okay. Each is corresponding to a specific period and a specific region of the aging. From the results, okay, in the previous tasks, CA will have proven that reflectometry can be used to detect local aging. Okay, reflectometry techniques would be used by maintenance operators to characterize local aging of cables under test, and for in situ inspection in a non-destructive way and all along this cable for a better safety and to save maintenance time in order to reduce maintenance cost. And excuse me?
No, go on, please.
I guess that's all.
What? Sorry?
Yeah, the presentation is done.
Okay, thank you.